3、2、1，开始。
My dear professor, our research is centered in Platonic polyhedron.
This is our introduction. First, in triangle ABC, we want to find a point S such that the sum of the distance of segment SA, segment SB, and segment SC is shortest, so we call point is Fermat point. Second, in a convex polygon with more than 3 vertices, we want to add some points S1, S2, etc. That we added is shortest, so we call point S1, S2 is Fermat point. The dark blue path is standard trees. This is our purpose. First, find the standard point in a regular polygon. Second, compare the shortest path from mathematical model and the bubble soap film found on the wild model. Third, find the standard point and the standard tree on Platonic polyhedron. This is our research equipment.
Material and method. In our study, we start from the standard tree of convex n-gon, and then generalize the standard tree of Platonic polyhedron. Now we are going to introduce the Platon graph. First one, triangle. There are two cases in triangle. First one is the largest angle is less than 120 degrees, and the second one is the largest angle is not less than 120 degrees. And our research we only use the first one. And the method is we choose segment AB and segment AC to make equilateral triangles, and then connect segment QC and segment BS, which intersect at point P. And point P is the Fermat point of triangle. And then the standard point of square. We consider the parallel side of square and make equilateral triangles and circumcircles. Then we connect segment EF, which intersect at S1 and S2. And they are the standard points of square. On the other hand, we choose point G as the gravity of square. Then we consider the Fermat point of triangle GAD and triangle GBC. And S1 and S2 are the standard points of square. And in rectangle, we consider the shoulder sides to make equilateral triangles and circumcircles. So S1 and S2 are the standard points of rectangle.
Now we're talking about Platonic polyhedron. This is our topic. Next we'll introduce the standard tree of tetrahedron. There are 4 faces, 4 vertices, and 6 edges in tetrahedron. By former experience, we use in square. We consider about triangle GAB and triangle GCD. We find the standard point is S1, S2. Then the red path is standard tree of tetrahedron. Next we will check the bubble foam film on the model. We made a couple wire model, which with each side is 10 cm and another one is 20 cm. We put it into bubble water, pour it upwards vertically and 45 degrees repeatedly. There are only one node inside. Since symmetric properties, we consider a node is gravity of the octahedron, tetrahedron, and then we found the distance is more than we had in mathematics. We figure out that the bubble soap form is minimum path and minimum energy structure. In 2010 American Journal of Physics, we want to find something to explain why the bubble soap form is not minimum path. We'll explore it later.
Now we are going to introduce the standard tree of hexahedron. We make a simulation on GeoGebra. First, we consider a standard tree of square and move it into the center of hexahedron. Then we consider these 4 rectangles. We make the standard tree and standard point of the rectangles, and then rotate them with an angle. And we found when the 4 rotate angles are equal 15 degrees, the blue edges will match the pink edges. So these 6 points are the standard points of hexahedron. In bubble solve experiment, we found there are only 4 knots in the hexahedron. And by calculus, we found the minimum path, which is larger than the result we found in mathematics.
Now we'll introduce the standard tree of octahedron. There are 8 faces, 6 vertices, and 12 edges in an octahedron. The 12 edges happen to be the edge of 3 squares. Each square has 2 standard points. So we have 6 standard points now. These 6 points just be vertices of our hexagon. After calculation, by inner product, we know each point connect the adjacent vertices of octahedron is 120 degrees. And this graph is exactly the bubble solve film of octahedron. But by our former experience, it should be 2 points less than vertices of polyhedron. So there are 4 standard points of octahedron. We want to remove 2 of them. So we remove the paths connected repeatedly the vertices of octahedron. Remove the paths which cause cycle. Finally, we remove two points. We remove 2 points, which is symmetric to the gravity of octahedron. Now we have and connect the tree, and now we have the standard tree of octahedron, which has 4 standard points and 9 edges in an octahedron. And then we make a mathematical model and find the result. Match our proof, and we show the proof on the test.
Now we are going to introduce the standard tree of dodecahedron. There are 12 faces and 20 vertices, and we have 2 methods. Method 1, we consider 8 vertices, which form a hexahedron, and there are 6 standard points of the hexahedron. And we divide dodecahedron to 6 samples and a hexahedron. Then we connect the red edges. So this is the standard tree of method 1. And method 2, we consider 3 golden rectangles. Each rectangle has 2 standard points. So there are 6 standard points, which form an octahedron. And there are 4 standard points of an octahedron. So there are 10 standard points now. But by our former experience, there are 20 vertices of dodecahedron. So it should have 18 standard points. So we choose the middle point of these 8 red edges to be the standard point. So there are 18 standard points of a dodecahedron.
Next, we'll introduce the standard tree of our hexahedron. There are 20 faces, 12 vertices, and 30 edges in an hexahedron. The 12 vertices is exactly the vertices of 3 golden rectangles. Each rectangle has 2 standard points. So we have 6 standard points, which is vertices of octahedron. By former experience, we know that there are 4 standard points of octahedron. So we have 10 standard points of hexahedron. In the same way, we use the judge bar to make a result, to make a simulation, and find a result match our proof.
Result and discussion. We show our result on this table. And compared with previous results, tetrahedron and hexahedron are known, and we verify the result. And the previous results of octahedron and dodecahedron are errors, and we revised the result. Then we propose the standard tree of hexahedron, which the previous result hadn't mentioned about it. And our concept to find the standard tree is we make a mathematical model in GeoGebra, and then we prove from standard tree of convex n-gon to 3 dimensions, and then compare with bubble sort experiment. And in 2 dimensions, the number of vertices of a regular polygon is phi, the number of center point is s, and then we have a rule of s equal v minus 2. And in 3 dimensions, the number of vertices of a platonic polyhedron is phi, and the number of center point is s. And suppose s equal v minus 2 also holds, then we can prove the minimum case we found. And our future prospects. We know the structure of adenovirus is an hexahedron, and standard tree has the minimum energy. So if we destroy the structure, maybe we can kill the virus. And we know there are many airports use the structure of polyhedrons. How can we spend this money and have the stable structure? Maybe we can consider about our result. And this is our reference. Thanks for listening.